Okay, we are going to be looking at 7.3, which is optimizing functions with multiple variables. Now, before we get into it, I want to do a bit of a review on optimizing. And we did this back in chapter 3 in 3.1, 3.2, and 3.3. So there's going to be some overlap on that of things that are familiar to us. So if you recall, we have a function y equals f of x. The first thing that we did was we found the critical numbers. So if you recall, CN represent critical numbers. Now we have to remember then, when do critical numbers occur? So we need to ask ourselves and review, when do critical numbers occur? Now, hopefully you recall from chapter 3 that they occur when the first derivative is equal to 0 or the first derivative does not exist. So if you recall, well, we're going to look at a picture here that hopefully will help jog your memory some. So after the critical numbers, we then looked at relative extrema. So what we were looking for was the minimum or the maximum. Now, what we did back in chapter 3 was we created a sign diagram. And if you recall, so you would have a number line. And based upon your critical numbers that you found up here, you would establish what your critical numbers were. And so those were here. And so if you recall, like if it was x equals 3, x equals 0, whatever those critical numbers are. Now, recall at the critical numbers, let's assume that the first derivative is equal to 0. So what that means is, if this is a critical number, then you have a horizontal line because the slope of a horizontal line is 0. So that occurred here at the critical numbers. Right here. All right. So that means here that the first derivative is equal to 0. And then what we did was we found a number over here and we plugged it in. We found a number here, plugged it in, and did the same thing here. And then when we plugged it in, we were looking for, is it a positive or a negative number? Because that would tell us if, let's say, if the first derivative, when you plug that in, was greater than 0, then what you know is that your slope is positive. So it's going up. Then it would hit this max. So this would be a maximum. And then let's say here that when you plugged it in at the first derivative, you got a number that was less than 0. So what that would tell us is that it is going downward. It hits 0, which means here would be a minimum. And then let's say the first derivative here was greater than 0. And so we know the slope would be going upward. So it gives us an idea of what is going on. Okay, so that's what the first derivative told us. And that was in our sign diagram. And then after that, what we did was we looked at the second derivative. And what that gave us was our concavity. So if the second derivative was greater than 0, then you know it concaves up. So it concaves up, which means then at this point you have a minimum. And if the second derivative is less than 0, it concaves down, which means here you would have a max. So that's what the first and second derivative test told us. Then we also got into and looked at what was called absolute extrema. Now, it's similar to relative extrema, except now you have a closed interval. Whereas previously, negative infinity and infinity, but now you have a closed interval. So you might have something like x is, we have 0 is less than or equal to x is less than or equal to 7. So these points here would be considered your end points. So you test your critical numbers as well as the end points in the original function, and the biggest number is your maximum and the smallest number is your minimum. So we did all of that in chapter 3. So now we're going to look at how that is similar, but then there are some differences that we have to do when we're talking about multivariable functions. So we're going to look at the steps we need to take. Sorry, I'm going to get my page up there. Okay, so what we're going to be looking at is extrema of multivariable functions. So that means we have variable x and variable y. All right, so the first step, we are going to find our critical numbers. Now, in chapter 3, we had to consider when the first derivative was equal to 0, and also possibly if it does not exist. With multivariable, we're only looking at when it's equal to 0. So there you go. It makes it a little bit simpler. So f sub x has to be equal to 0. F sub y, we will set equal to 0. So what we will create here is a systems of equations. Now, systems of equations is something that you would have done in college algebra or algebra for STEM. If you did not have that class, you may have to put in a little bit extra work just because it won't be as familiar to you. All right, the second step, evaluate at the second derivative. So what that means is you're going to take your critical number. So I'm just going to assume or suppose that A being some number, B being some number, is a critical number. So this right here would have been what you found up here in step 1. So then what you're going to do is you're going to take these two numbers or this ordered pair, and you're going to find f sub xx at that point, and it will equal some number f sub yy at that critical number, and f sub xy at that critical number. And then these will be numerical values, okay? All right, so that's step 1, step 2. That brings us then to step 3, which is what is called the d-test. And the d-test is when d is equal to f sub xx, so it would be this value right here, times f sub yy, this value here, minus f sub xy to the second power. Now, the results of this is going to help us find whether we have a minimum or a maximum. All right, so let me see. I want to show you something here a minute, and I was trying to find the picture of it. Okay, so when you plug this in, these values in, you're going to find out what D is. And then the results of that are going to help you establish your results. So if the D test, this value here is a value greater than 0, and f sub xx is greater than 0. So this is greater than 0, and this is greater than 0. Then that critical number is a minimum. And I want to show you what it would look like. That is this picture right here. When D is greater than 0, f sub xx is greater than 0. See that point right there? That is considered a minimum. Okay. All right. If D is greater than 0 and f sub xx is less than 0, then that critical number is a maximum. And here's what that would look like. As you can see, with two variables, we're looking at a three-dimensional picture. So we have D came out greater than 0, f sub xx was less than 0. So it looks like this, where that point then would be a maximum. Now, we've dealt with minimum and maximum. Now I'm going to throw something else in there we haven't seen before. If D is less than 0, if it's less than 0, you don't even have to worry about what f sub xx is. Then that critical number, it's what is called a saddle point. So I want to show you what that looks like. And as you can see, it looks like a saddle. It looks like you could just put that on a horse and jump on and ride that. So this point here is what we would call saddle point. So that is something new and different with multivariable functions that we didn't look at previously. We didn't have to encounter. Okay, so now let's look at an example and go through all of those steps. All right. So I'm going to give you a function, multivariable, of 3x squared plus y squared plus 3xy plus 3x plus y plus 6. All right. Step 1 was to find your critical numbers, which basically means we need to find the first derivatives with respect to x and then with respect to y. So f sub x would equal, this would be 6x. This would be like a constant, so that would be 0. This would be, let's see, x, that would just be 1, so we would get plus 3y plus 3 plus 0 plus 0. So that's what we get here. So f sub y, this would be 0. This would be 2y to the first plus 3x plus 0 plus 1 plus 0. All right. So then these are the two equations. And we need to set these equal to 0. I probably should have gone all the way out, but that's okay. So, because remember, at the first derivative where they are equal to 0, that is where we have our critical numbers. All right, so this is a system of equations. So in these, we have to solve this system for x and for y. So if you think back to your college algebra or algebra for STEM, We did it substitution method or the elimination method. Elimination method is also known as the addition method. So what I'm going to do first is I'm going to put the constants on the opposite or the other side of the equal sign. So for this first equation, I would subtract 3 from both sides. So I'm going to get 6x plus 3y equals -3. And then on this equation, I'm going to subtract 1 from both sides, as well as I'm going to line up my variables. So this would be 3x plus 2y equals -1. So in the elimination method or the addition method, we want either our coefficients of our x terms to be opposites, or we want the coefficients of our y terms to be opposites. So what I'm going to do is I'm going to eliminate my x's. This is 6. I can multiply 3 times -2, and that would give me -6. Now, don't forget, you have to multiply this -2 times every term in this equation. So the first equation I'm going to leave alone. Now I'm going to multiply each one of these by -2. So I would get -6x minus 4y equals 2. Anything minus itself is 0, so that is gone. 3 minus 4, that's -1y or -y equals -3 plus 2 is -1. I don't want -y, I want just y, so I'm going to divide both sides by -1 and I get y equals 1. So there is the y value. Now I need to find the x value. So I'm just going to go to this equation right here, and in place of the y, I'm going to substitute in 1. So that would give me 6x plus 3 times 1 equals -3. So I get 6x plus 3 equals -3. I'm going to subtract 3 from both sides because I want to move this one over here. So I get 6x equals -6, divide both sides by 6, and I get x equals -1. All right, so now I have my x value and I have my y value. So we have found our critical number, and that critical number is the x coordinate and the y coordinate. So here's my critical number. All right, so then step 2 is your second derivative test, or not test, but finding the second derivative. And we're going to do this at -1, 1. Okay, but what that means is if there is any variables left in the second derivative, we would substitute these in. But let's take a look at what happens. F sub x, x. All right, so I come up here and I'm going to take the derivative with respect to x. So that would be 6 plus 0 plus 0. So I just get the numerical 6, so I don't have to plug in anything with these values. It just gives me a numerical value. If this came out and was 6x, then in place of x, I would put -1, but it didn't. All right, f sub y, y. All right, so this one with respect to y, so that would be 2 plus 0 plus 0. So again, we just get a numerical value. Then f sub x, y. So I come back up here to this one, but now I'm going to do it with respect to y. So that would be 0 plus 3 plus 0. So all of these gave us just a numerical value. That makes it pretty easy. But again, if I would have gotten a variable like 2y, then I would take 2 times the y coordinate, which is 1. Okay. All right. So now that brings us to the third step, which is the D test. And remember what that is D equals f sub xx times f sub yy minus f sub xy squared. So my D would be 6 times 2 minus 3 squared. So I get 12 minus 9. So I get 3. All right. So now we are going to consider what our results are. So now is where we look at here for the results. So I look at this and I'm going to look at my, if you remember, we're going to look at what D is and what f sub xx is. So I go, okay, my D is positive, so it's greater than 0. And f sub xx is also greater than 0. Therefore, at the critical number, -1, 1, we have a minimum. So we are going to take the original function at the critical number, -1, 1, and find out what that minimum is. So I would have 3 times -1 squared plus 1 squared. Yeah, for a minute I thought it was cubed. Plus 3 times -1 times 1 plus 3 times -1 plus 1 plus 6. And I calculated that, but I want to make sure I get the same answer. So we have 3 times -1 squared plus 1 squared is 1 plus 3 times -1 times 1 plus 3 times -1 plus 1 plus 6, and we get 5. All right, let's look at another example. All right, f sub xy is x squared plus y cubed minus 6x minus 12y. All right, step 1, critical numbers. So f sub x would equal 2x plus 0 minus 6 minus 0. F sub y would be 0 plus 3y squared minus 0 minus 12. All right, so when do we have critical numbers? When these are equal to 0. So these are the two equations that we need to solve for x and y. Now notice here that they don't both have an x, they don't both have a y. The first one has an x, the second one has a y squared. So we're not going to do it by using the elimination method or the addition method. If you'll look at that first equation, 2x minus 6 equals 0, I can take that equation and solve for x. So I'm going to take that first equation and solve for x. And we get x equals 3. The second equation has a y squared, so I'm going to take that equation, 3y squared minus 12 equals 0, and I'm going to solve for y. So the first thing I'm going to do is add 12. I'm going to divide by 3. Now, to get rid of the squared, you have to think back to algebra. And we do the square root property, which means we take the square root of both sides. But here's where you have to be careful. This cancels this and we get y. But over here, you have to consider plus or minus the square root of 4, which is plus or minus 2. And the reason is because positive 2 times positive 2 is 4, negative 2 times negative 2 is 4. So if you'll notice, we have two possibilities for y. All right, so how does that affect our critical numbers then? Well, I have one possibility where x is 3 and y is positive 2. I have another critical number where x is 3 and y is negative 2. So here we have two possibilities. All right, so let's look at how that affects what we do in our next steps. All right, step 2, second derivative at my critical numbers. Okay. All right. So come back up here. Let me make sure we can see it. So I am going to find the second derivative, f of xx, which would be 2. Okay, just got a number. All right. F of y. So this with respect to y, we would get 6y. So notice we have a variable here, minus 0. F of xy would just give us 0. All right, so let's pause and take a look at this right here. So let's look at it with respect to the critical number 3, 2. So we're going to substitute in the y value, which is 2. So that would give us 12. And then at the second critical value, which is 3, negative 2. So that would give us 6 times negative 2, which is negative 12. Okay. All right. So that brings us to the D test. Now, if you remember, it's f of xx times f's of yy minus f's of xy squared. So what that gives us is 12y. Okay. All right. So let's look at the critical number 3, 2. So my D would be 12 times 2, which is 24. All right, so what are the things that we look at? We go, okay, D is positive, so it's greater than 0. And f of xx is greater than 0. And so if they're both greater than 0, then that tells me that this is a minimum. And it is a minimum at the original function. So we would have 3 squared plus 2 cubed minus 6 times 3 minus 12 times 2, which, so 3 squared is 9, plus 2 cubed is 8, minus 6 times 3 is 18, minus 12 times 2 is 24. So we get negative 25. So this is where you have a minimum at. All right, we now also have to do it for point or critical number 3, negative 2. So my D is equal to 12 times negative 2, which is negative 24. Now, this is a negative number, so D is less than 0. So I don't even have to consider f of xx. As soon as that is, the D gives me a value that is less than 0, I know that this is a saddle point. Now, where is it a saddle point at? 3, negative 2. So now I have 3 squared plus negative 2 cubed minus 6 times 3 minus 12 times negative 2. So this gives us 9. Negative 2 cubed is negative 8. So I'll have minus 8, minus 18. And now I'm going to have plus 24. So I get 7. So that one looked a little bit different. All right, we're going to look at one more example that is an application problem. Okay, now, let me look at something real quick. Sorry about this. Okay. I'm just making sure I have the right. Okay. So what we're looking at is profit in thousands of dollars per hour. And let's see, we are talking about compact and midsize. So we're going to let X be our number of compact cars made per hour and Y be the number of midsize. Okay. All right, so you are given, let's assume you're given the price function for the compacts. So compacts is your X variable, and you are given 17 minus 2X. So if we knew the number, we would substitute that in and find the price. And then for the mid-size, you are given, let's see, 20 minus Y. Okay. All right, so here's the question being asked. Find the number of cars of each that maximizes profit and then find that profit. Okay. All right. Now, in order to do this, to maximize profit, okay, so if you recall, profit is revenue minus cost. What you bring in minus cost. Okay, so that means that we would need to be given the cost function as well because they're not giving me the price function. So the cost function is given as 15x plus 16y minus 2xy plus 5. Okay, all right, so you're given the cost function and you're given the price of the compact or the price function for the compact cars and the price function for the midsize. Okay, so we're dealing with profit and we want to know when it maximizes. Okay, so maximize means, hey, we're going to deal with critical numbers, but I first need my profit function because I don't have my profit function. All right, so your profit function is your price times number of compact cars. So if you have one compact car, then you would substitute that in if you had two and so forth. So it is price per how many that you're producing plus, now we're dealing with midsize. So the price per how many of them are produced. And then you remember, so this is your revenue. So there's your revenue, what you're bringing in. Okay. So then we have to subtract our cost function. And our cost function is 15x plus 16y minus 2xy plus 5. All right, so to get this cleaned up a little bit, I'm going to distribute. So I would have 17x minus 2x squared plus 20y minus y squared minus 15x minus 16y plus 2xy minus 5, because we have to distribute that minus through. Okay. All right. So just cleaning it up a little bit more. I'm going to put my squared terms first. So negative 2x squared minus y squared. And then we're going to combine, well, let's do our 2xy next, plus 2xy. So we've dealt with that, that, and that. So then 17x minus 15x, so that would give me plus 2x. And then I have 20y minus 16y, so that is plus 4y minus 5. So all of that was done to get us to our profit function, because we had to get that profit function because it said profit here. If it had said cost, then we could have used this cost function. But because it said profit, then I had to find that actual profit function first, which I do know one of your problems in WebAssign, you're going to have to do this. Okay, so now we're going to maximize this. So now we need our critical numbers. So in order to find my critical numbers, then I'm going to find piece of xx. So I'm going to take this and find the first derivative with respect, whoops, what am I doing? I'm not doing the second derivative. With respect to x. So this would be negative 4x. Goodness, I can't write now all of a sudden. And this would be 0 plus 2y plus 2 plus 0 minus 0. Piece of y would be 0 minus 2y plus 2x plus 0 plus 4 minus 0. So now what we're going to do is we found our first derivatives. And so if you remember, we set these equal to 0. And we look at these. And in this case, they both have an x and they both have a y. So we're going to look at this as a systems of equations. So when I look at this and I go, okay, I'm going to rewrite this one by moving my constant over here. So I'd have negative 4x plus 2y equals negative 2, subtracting 2 from both sides. Then I'm going to subtract 4 from both sides, and I'm also going to move these to where my variables are lined up. Wow, I like this. Look at your y's. They're already opposites. So I can go, okay, that's a 0. So I would have negative 2x equals negative 6. Divide both sides by 2, so x equals 3. So then I'm going to take this and substitute it in. I'm just going to substitute it into the first one. So I'd have negative 4 times 3 plus 2y equals negative 2. So negative 12 plus 2y equals negative 2. So I'm going to add 12 to both sides. So 2y equals 10. So y equals 5. So now I have my critical number. I'm just going to put it in between these. So my critical ordered pair is 3, 5. All right. So now what we need to do, we did critical numbers. That's the first step. Second step is the second derivative. So let's see. Yep, we need to be able to see this. So now we're going to do the second derivative, p's of x. So the first derivative with respect to x, that would be -4 plus 0 plus 0. Piece of y would be -2 plus 0 plus 0. And piece of xy would be 0 plus 2 plus 0. So this is nice. They all come out as just numbers. So we need to, now notice we are seeing what maximizes profit, right? So we have to prove or show that this critical number is a maximum. That's why I'm going to now do the D test. So this was step 2. This is step 3. I'll come up here finding the critical numbers. This was step 1, if that's helpful. All right, so if you remember, the D test is D is equal to piece of XX times piece of YY minus piece of XY squared. So we get 8 minus 4, which is 4. So we go, okay, D is greater than 0, check. What's the other thing that has to be greater? Or I'm sorry, not greater than 0, because if this was greater than 0, we would have a minimum, and we're showing it's a maximum. So piece of XX is less than 0. So because these two things occurred, we know our critical number is a maximum. So it tells us then to find that profit. Well, to find that profit, we take our ordered pair, which is our critical number, and we put it into the profit function. So it would be -2 times 3 squared minus 5 squared plus 2 times 3 times 5 plus 2 times 3 plus 4 times 5 minus 5. Woo! So when you plug all of this into your calculator, it equals 8. Now here's where you need to be careful. Does that mean our profit maximizes at $8 per hour? Don't forget thousands of dollars per hour. So when you get 8, that actually means it maximizes profit at $8,000 per hour. Not too shabby of a gig to be getting profit of $8,000 an hour. So I can tell you as a teacher, I am not getting that. So there you go. That is 7.3.